In this module, we're going to be learning about significant digits. When we are working problems, we are often given the numerical value for various quantities. The precision with which these values are known varies, and the precision of each of the numbers used in a calculation actually impacts the final answer. Now, we know that rational numbers can be used to represent values exactly. That is, they have infinite precision or an infinite number of significant digits. But not all numbers can be expressed as rational numbers. Pi, for example, has an infinite number of digits needed to represent it. Such values, if we want to write them down, can only be expressed with a finite number of significant digits, and therefore has some error inherent in the quantity we write down. Now, much more important to us is the fact that measured quantities will always have a finite precision because there is always uncertainty in measurement. Such values are also represented with a finite number of significant digits. Now, for us, it's not going to be important to learn at this time how we determine from measurement what the number of significant digits is in the measured values. What we want to understand here is how the number that is presented tells you which digits are and are not significant. We also want to learn about the rules used when we're calculating with numbers with finite precision to determine the precision and the number of significant digits in the final answer that we compute. Now, here are the basic rules. All digits in a given value are significant except the following. So, any leading zeros are not significant. For example, 083 has two significant digits, the 8 and the 3. The leading zero is not significant. The same thing is true for 0.0083. It has the same two significant digits. The other zeros are just placeholders. Any trailing zeros that are used only to designate the scale of the number are also not significant. For example, the number 634000 has at least three significant digits, but we actually need more information to know exactly how many significant digits there are in this number. Now, if we place a decimal point at the end of all those zeros, then that actually means that all those zeros are significant, and there are 6 significant digits. But if we don't have 6 significant digits, but we have more than 3, we can't use a decimal place, at least in this form of notation, to tell us exactly how many digits there are. But what we can do is switch to using exponential notation, and then we remove the ambiguity. So the same number with 4 significant digits could be expressed, for example, as 6.340 times 10 to the 5th. In this example, that last zero is now a significant digit. That is, all zeros to the right of a decimal point are significant, so long as there is a non-zero digit to the left of the decimal. Otherwise, the only digits to the right, or the only zeros to the right of a decimal point that are significant are those which are to the right of the first non-zero digit. All right, to understand this, let's look at some examples. So here are a set of numbers here, and I want you to think about, for each example, how many significant digits are represented. And I'll give you a moment to think about each example. So for the first one, 15.00, how many significant digits does this number have? And if you came up with 4, then you're correct. The next number, 003, how many significant digits? In this case, there's just one significant digit. The next example, 0.00054. And the correct answer in this case is two significant digits, the 5 and the 4. The next example, it's the same quantity, 0.00054, but now there are three trailing zeros. How many significant digits? And the correct answer this time is 5. The next example, how many significant digits in 10.00001? And if you've had time to add that up, it's 7 significant digits. The next example, 29000 point. I think we all have this now. This has 5 significant digits. And the last example, 29000. How many significant digits? Well, if you're sitting there scratching your head, that's good, because this is a little bit ambiguous. There are at least 2 significant digits, but we don't know for certain how many significant digits there are in this number. We can get around this, of course, by using exponential notation. So here's that same number, 29,000, expressed in several different ways, each of which is now giving a precise number of significant digits. And how many significant digits are in each of the examples? So, first example, 29.0 times 10 to the 3 has 3 significant digits. Now, if we express this as 290 times 10 to the 2, again, it has 3 significant digits. Let's make our exponent 10 to the 4, then we need to write this as 2.900 times 10 to the 4, and in this case we have 4 significant digits. Now we can also do the same thing without a non-zero value to the left of the decimal, so 0.00290 times 10 to the 7, it's still 29,000, but in this case it has how many significant digits? 3. Next example, 0.02900 times 10 to the 6 has 4 significant digits. The next example has 5 significant digits, and the final example has 6 significant digits. Now, we can also refer to the most and least significant digits in any given value. All right, the most significant digit, it's the digit with the highest exponential value, that is, the leftmost digit in decimal notation. The least significant digit is the digit with the lowest exponential value, that is, the rightmost digit in decimal notation. So let's return to our examples. And for each of the examples we looked at before, we're marking the most significant digit in red and the least significant digit in blue. And these are all given in the first column of our 2 sets of examples. So for example, in 15.00, the 1 is the most significant digit, and the final 0 is the least significant digit. In the next column, we're giving the exponents for the most and the least significant digit. The 1 is in the tens column, that is, in the numbers which are obtained from 10 to the 1, 1 times 10 to the 1 in this case. So this is in the 1 exponential column, and the final 0 is in the column for 10 to the minus 2, or 1/100th, is the minus 2 exponential value. The next number, 003, well, the most and the least significant digits are the same. They're in the 0 exponent column. The next number, 0.00054, has the most significant digit with an exponent of minus 4, and the least significant digit exponent of minus 5. Now, one thing you may notice here is if you take the value for the exponent for the most significant digit, which in this case is minus 4, subtract from that the exponent for the least significant digit, minus 5. So we're going to subtract minus 5 from minus 4. That gives us 1. And then if we add 1 to it, that gives us 2. That's always going to be the number of significant digits. So it's the exponent of the most significant digit minus the exponent of the least significant digit plus 1. And if we look at the remaining examples, we see each one of those listing out the exponent for the most and least significant digits. And notice that in the right column of examples, we have exactly the same number being represented. And so the most significant digit is always the same in this case. Even though it's occurring in various different columns, we have to take into account that we're using exponential notation. So there's a 10 to the sum power being multiplying each example. But I think you get the idea. All right. Now, what happens if we do arithmetic with significant digits? Well, when we apply arithmetic operations to values with finite precision, we must determine which digits in the answer are significant. So for multiplication and division, when we multiply or divide two values, the result will have the same number of significant digits as the value with the least number of significant digits. Some examples will help here. So we multiply the numbers 123.7 times 0.013, and we get 1.6081. That's the full answer. But if we look at the most and least significant digits in each number, we see the first number has 4 significant digits, the second number has 2 significant digits, and therefore our result will have 2 significant digits. All right, so the 1 in 1.6081 is our most significant digit, the 6 is our least significant digits, and the remainder of the digits are not significant. Now, if this were the final answer we were going to present, we would round this to 1.6. But it's very important to keep in mind that if you're going to use this number in additional calculations, you don't want to do the rounding at this point. This is a mistake that students often make when working long problems, and when then checking their answers against the correct result, they find there's something wrong. And really, the only thing they've done wrong is they've rounded their numbers prematurely, and this causes an accumulation of error. So you want to only do the rounding at the very end. Keep as many digits in your intermediate calculation as you can, and round at the end. Now another example here, we can multiply 123.7, this time by 0.032. We see what the final answer is, 3.9584. Again, we have 4 and 2 for the significant digits in the two numbers going in. So the final answer is going to have 2 significant digits. And this time when we round it, we have to change both of the values in our final answer to 4.0, but we get 2 significant digits here. Addition and subtraction has slightly different rules. It's a little bit more complicated here. When adding or subtracting two values, the exponent of the least significant digit in the result should be the same as the largest exponent, that is the leftmost digit, from the least significant digits being combined. Let's look at an example. 123.7 plus 0.352. The full answer is 124.052. Now, if you look at the individual numbers going in, we see for the first number, it has its least significant digit in the -1 exponent. The second significant digit has its least significant digit in the -3. So our answer is going to have its least significant digit in the largest of the least significant digits, that's -1. So our least significant digit is the digit just to the right of the decimal place. And again, if we're rounding to our final result, we get 124.1. But remember, don't round to your final result until the final answer. And a very important final example, let's look at subtraction here. We have 123.7 minus 122.75. We get 0.95. Okay, where are our least significant digits? Well, the largest one is, again, in the -1 column. So in our answer, that's going to be the 9. That's our least significant digit. And it looks like we have only one significant digit in our final answer, even though the numbers going in had 4 and 5 significant digits going in. We can get subtractive cancellation, which can significantly reduce the precision of the numbers that we get. So subtracting numbers which are nearly the same can severely decrease the precision of your calculations. In this case, it looks like we have only one significant digit, but actually, when we round this, we round up to 1.0, and we see that there are actually two significant digits in the final answer. All right, I hope that helps you understand how to deal with significant digits.